these additive chemicals you bring in there. All they do is also supposed to, on a chemical level, generate these free electrons to react with your water. But in this case, you can directly generate the free electrons using a particle accelerator. And like I said, when reaching out to general public, a common question, of course, and it's a little bit of a hesitation when you introduce into this technology is like, but does my water get radioactive? You want to irradiate my drinking water somewhat down the treatment line eventually. So, of course, people are somewhat hesitant to think that that might be a good idea. And the really takeaway or take-home message here also I want to emphasize in my talk here today is no. So there is a threshold to the energy that we can bring these electrons in our particle accelerator to. Obviously, in science, we go well beyond that. But for these applications, we always want to stay below 10 mega electron volts, so 10 MeV, because that is the neutron generation threshold in water. If you go above that threshold, you would start generating neutrons, and those would activate in a radioactive sense your water. But if you stay below that, you can really just generate your free radicals and break down the contaminants in the water. So that's kind of the safe side you want to stay on. So now, like I said, going through a little bit of history. So we obviously here at Jefferson Lab, or we don't want to claim credit that we're the first ones to think of using particle accelerators to irradiate water. This already started in the United States in the early 80s, actually. And that started at the Miami E-beam research facility with this guy over here, who back then treated wastewater. You see him here in the trailer, or they had a trailer system where they could run wastewater through and had a small normal conducting accelerator at the Virginia Key. So not to mix up with the state of Virginia, this is still down in Florida at the Miami, or the Miami E-beam research facility was the university-based site of that. And Bill Cooper, that's his name of the guy over here, he then also reached out to the local Virginia Key, that's district in Florida, wastewater treatment plant, to then on a larger scale in an actual wastewater treatment plant, use this technology he had developed at the E-beam research facility and see what kind of contaminants he could break down with this. And what he generated, their publications from back then are really long lists or tables in which you can really see all the typical suspects, the typical contaminants you have in drinking water. And then on the other side, what kind of dose, the minimum dose that is required to deliver with a particle accelerator to break them down in water. So that's a really nice sort of lookup research and classic first step invention or kind of investigation into how you can utilize technology, generating tables to see, okay, that's the minimum dose that is required to break them down. But Bill Cooper went further, and with two of his colleagues, Tom Wade and Chuck Hirsch, he also then founded his high voltage environmental applications company, Incorporated, that basically was developing these flatbed truck based compact systems, late 80s then. So he started in the early 80s with the research, and in the late 80s started that company to drive around and deliver this electron beam to different facilities and offer that as a service to irradiate the water and break down these contaminants. Unfortunately, that on the business side didn't really take off right then. It was somewhat, if you talk to Bill, we are still, he's a retired professor now down in Florida, but we're still in touch with him when we now try to pick up this technology again and try to bring it to the next level. But when you try to understand why that business eventually, unfortunately, failed on his end, is that it was quite ahead of its time. There were some regulation issues also with the Environmental Protection Agency back then, as they required much higher doses than what he had shown and proven that are used or required to break down these contaminants. So in the end, it wasn't really feasible anymore. And like I said, it was somewhat ahead of its time, and it didn't really pick off in large scale. Also due to, of course, the limitation of the normal conducting technology that they were using back then. So kind of fast forward into the now and here, if we look at Asia and in those places, we are most, or in particular, looking at facilities that were started in South Korea. So this is early 2000s or mid 2000s, actually 2006 in South Korea. There was a first pilot project at a industrial dyeing treatment or dyeing textile industry plant, where they used to have their local treatment plant for the water that was obviously heavily contaminated from the textile industry on that site. And there they then integrated an electron beam facility also based on normal conducting technology to break down the contaminants in that industrial wastewater. But moving forward also recently, with support from the IAEA, so the International Atomic Energy Agency, in terms of doing the fundamental research and technology development in China, there were multiple plants. There's an example here of 2020, where in a knitting factory, again in the textile industry, they set up a total of 7 picture over here on the right, we can see that the 7 machines of 7 particle accelerators, again, used to treat the industrial wastewater generated by that facility. There are many more examples, especially in China. This technology has really taken off. So it's something, like I said, pioneered in the US somewhat in the 80s as a first idea. Back then, didn't really take off. But now it's finding its way back into especially the heavily contaminated wastewater, industrial wastewater of textile industry. And where is that textile industry located in our days these days? And that's mostly Southeast Asia and, well, North Asia, somewhere up there in Korea too, but also in China. So that's why it makes them a prime customer for this technology. When we look at the technology that is in use for these treatment facilities that are out there right now, like I said, they are based on kind of conventional technology. So they're mostly high voltage DC accelerators. Over here, this is actually a cross section of a 3D model of what one of these irradiation units at the South Korean plant from 2006 looks like. So you generate a high energy electron beam up here, and then you split that in multiple beam lines. And down here, you have multiple beam horns, and there's a constant stream of water being passed by these beam exit windows, where your electron beam is then introduced to the water, like I said, breaking it down or generating these highly reactive oxidants and reductants in the water, which then attack your contaminants from the textile industry that were brought into the water in the first place. But somehow my slides are not advancing. Well, they're slowly advancing over here, but that's, okay, that was on purpose. Actually, that's a picture of the actual facility. So you see the same part, what you see down here, real life picture. And all these accelerators that are in use there are mostly based on so-called ELV type machines that were developed at the Butker Institute of Nuclear Physics in Russia in the 70s and 1970s. They're usually delivering an electron energy of 1 to 2 MeV. Quick reminder, as we earlier said, you want to stay below the 10 MeV, not to radioactivate your water. So 1 or 2 MeV, you're definitely on the safe side, and something like a few tens of kilowatt of beam energy as an output. So if you then want to go to a larger facility, more throughput of wastewater, you obviously need more power, and you do that by scaling and adding multiple machines. Again, the same picture from the page before, as for an example from this Chinese facility where they have a total of 7 accelerators based on this ELV type. These are variations developed by a Chinese company that they put in place there, delivering then up to lower hundreds of kilowatt in total beam power to treat the wastewater. Now, switching gears, like I said, lesson number 2, RF particle acceleration. As I've shown you on the slide before, these are machines that are also Butker Institute of Nuclear Physics, Fundamental Research Institute, developed for basic science, but in the 70s. But then the obvious question is, how do science machines nowadays actually reach much higher energies and also much higher power throughput? And the answer to that is radio frequency particle acceleration. So the machines, what you've seen before, DC, direct current, normal conducting machines. I'm not going to emphasize normal conducting too much because radio frequency can also be normal conducting in its start. But they're DC machines where you put a high voltage to accelerate those electrons, and then you're limited at some point how high you can go with your voltage. The radio frequency principle for particle acceleration is based on so-called cavities. And these are not the cavities that you typically find in your teeth and that we're all afraid of when we go to the dentist, but these hollow metallic resonators. So the idea is that you can build those. What you see here is an example of a single cell cavity. So you have beam tubes left and right. This is the set normal conducting, a copper structure, but you're not limited. You can also go to, for example, 2-cell and higher numbers of cavities. And to understand now how RF acceleration works, we have to look at these cells. So really that's the main magic, or that's where the magic, so to say, happens, where we do accelerate our charged particles in those cells. So to simplify that as a quick excursion, you have a metallic resonator, as I said before, that's defined, or we call that a cavity. You have a simple example, like the example, the picture you've seen before was a 2-cell resonator. So here in the background, you now see your 2-cell structure, like I said, 2D representation of that. And what happens now is that we introduce a radio frequency signal, so a radio frequent wave, electric wave in that hollow. This is under vacuum resonator. And what happens then is that you create a so-called standing wave in that resonator. And that looks something like that. And over time, this wave does nothing but, in this mode, as a standing wave, it oscillates in these 2 cells. So you go through and you reach the same level that we were before. And suddenly there's something new in here. This is an electron bunch. So if you now introduce an electron bunch into that standing field in your resonator, you can accelerate it. You might ask at this point, how do you get the electron bunch in there in the first place? And of course, I could give you the simple answer and say that's a government secret, which scientists don't like to give away. It's just a joke on a site. So the really simple, again, to stay on a nutshell level idea of how to generate that is, if you look at a man having an idea here, usually visualized by light bulb, is really just exactly that. You can use the thermoelectric effect, and by heating up a wire in such a light bulb, for example, you will generate free electrons. So if you now have something like this, so an electron source on one end, and on the other end, your hollow resonator, your cavity, you still have your standing RF wave in there, as we've introduced it in the first place. You bring that electron into the cavity, then the magic of particle acceleration happens. And the way you can visualize that again is that this electron now sees a downward slope in this field if you look at this 2D representation. So it's being dragged down into the valley of this field in the first cell of that resonator. And what happens with the field, as I've shown before, it is oscillating in that cavity while the electron bunch travels inside the cavity, is that you see it go down, the field slowly changes. By the time the electron bunch has reached the center of that cell, the field is basically flat, not accelerating anymore, but now it's flipping its sign. So it is slowly building up that hill that is pushing out the electron bunch into the next cell. And there you see basically the repetition of the situation you had before. As soon as the electron enters, or the electron bunch enters the next cell, you will again see a downward slope dragging the electron into that cell. So really what happens there is nothing but a constant. You can continue that to the next cell, continuation of a pull into the cell and a push out of the cell into the next cell. So now we've understood RF particle acceleration on a simple topic. And with Monty Python, as I like to say here, now for something completely different. And that is, as I said before, Jefferson Lab, us as a national science lab here in the United States on the East Coast, doing research in the particle accelerator realm. So who we are, quick introduction. We are one of the Department of Energy 17 national labs in the United States, and we are pretty much one of the main nuclear physics hubs. We are located over here, like I said, on the East Coast in the beautiful Commonwealth of Virginia, directly at the Atlantic Ocean. City is Newport News in Virginia. We're established in the 1980s, so pretty much same time that this electron beam treatment was developed down in Florida by Professor Bill Cooper. And back then, the Jefferson Lab, which was actually not called Jefferson Lab, it was called CBAF, was exactly established to host this facility. CBAF stands for Continuous Electron Beam Accelerator Facility, and that was one of the first large-scale machines utilizing superconducting radio frequency, and I'll get to that in one of the next slides. Currently, we have about 900 employees, or even above 900 employees. We're really strongly going towards 1,000. Over 1,900 active staff and students, lots of grad students that produce their PhDs in nuclear physics with experiments at our machine. And our main mission, you can quote from the website, has multiple elements to it. I got them all down here, but I want to really highlight this center one here, because that one is, or emphasize that we have the mission to apply advanced particle accelerator technology, detector and other technologies to develop new basic research capabilities. That is basically CBAF, the nuclear physics discovery machine we're operating and maintaining, but also to address the challenges of modern society. And that's obviously the reason I want to emphasize that, because with the title of the talk, as I said, from the lab to your sewage plant, we want to develop technologies that don't just tackle the nuclear physics fundamental research, but also challenges of modern society, like the handling of wastewater, and bring them out of the lab into real life applications. So quickly looking into how old we are, if you've done the math right, you remember we were founded in 1984, then yes, in this year of 2024, we actually got reason to celebrate. We had a big motto party, so to say, and introduced this motto of Virginia is for science lovers. That's derived off of a classic state motto that Virginia is always, we all have that on our car plates driving around here. Virginia is for lovers, and like to, in this particular year, put the focus on us as a national lab as Virginia is for science lovers. And you see over here, that was one of the official PR pictures, Jefferson Lab celebrating 40 years of research and discovery. You see a nice aerial picture of what the lab looks like. So the lab is down here. This is the facility here over the test lab that me and Dr. Dakal are working in, and this is here the ground of the CBEF accelerator, and it's a really nice picture. I'd like to also see the link. We are, like I said, positioned right at the coast, and we also have a big river here in the background. So there's a lot of water around Jefferson Lab, so it really makes sense to utilize our technology to tackle water-related topics in that research. But then drawing the link from Jefferson Lab to particle accelerators, obviously, like I said, we built and operate particle accelerators. Our main piece of equipment, the CBEF accelerator, this is what it looks like. This green little block here in the beginning is supposed to be the injector or represent the injector, so the light bulb that I showed you in an earlier slide. And what you see here is the north LINAC, and this is the south LINAC. And what happens then with the electrons, they go into here, there's RF, actually SRF, particle acceleration. So again, the concept I just showed you in the earlier slides, and they're being accelerated through this LINAC here, and then you see these arcs. These arcs are used because we kind of use it in a racetrack pattern going over multiple turns of that machine. And every time the electrons pass through this LINAC, same for the north as well as the south LINAC, we will increase their energy, and then they have to go through a different arc. So they kind of, this is blown up here in this proportion. They go through a first low energy arc, then they go to the next level, and then they start going through the next higher arc, and they keep going through these LINACs, and these arcs going higher in energy up to 12 giga electron volts. So that's significantly higher than the 10 mega electron volts that I showed you earlier. You want to stay below for the wastewater treatment for running those nuclear experiments. And eventually they end up in these so-called experimental halls, A, B, C on one end, and then after yet another path through the North LINAC into the hall D2. As you can tell, I mean, this is the aerial picture, kind of similar to the one I've showed you in the slide before, where you can see the above ground structures of that machine. So you can kind of tell where the North LINAC is here and where the South LINAC is. And they're highlighted these big kind of like the hills where they're underground caves too, where we have those experimental halls. So these bumps you see above ground here kind of represent these bumps you see on top of those. So it's much more structure underground. As I also told you, 12 giga electron volt is the peak energy of this machine. 10 MeV is sort of the safe side you want to stay below when you treat wastewater. So this machine obviously is not perfectly designed to treat wastewater. And we do have to deal with radioactivity and activated elements, which is also the main reason why the whole facility is brought underground. What you see here above ground, like I said, where you can kind of tell where your structures are underground, are mostly supply buildings that supply this RF field that we have to pump in the cavities underground to accelerate the electrons. And what you have here in the center, represented by these couple of blocks, and you see also the structure over here, is then the cryo plant running the whole facility. And I'll get to why that is needed in the next slides, talking about superconductivity. But obviously, then the next question when you see CBAF, our big machine, is you ask us, where do we build them? And that is the Jefferson Lab SRF Institute, where both Dr. Carl and me are working. And that's really sort of our pride institute here, where we build particle accelerators for all kinds of different labs around the nation. If you now ask, what is SRF? I mean, I've already given it away by my introduction. I always like to bring in, and of course, this stands for super rich and famous in that case. And I took one AI generated picture here over on the site. And just as a little side remark, if you ever ask yourself how far we've gotten with AI, when you ask for AI to generate a picture of super rich and famous, obviously AI doesn't really know how many arms usually a human has. So it took me a moment to realize that one of these persons has more than the usual two. But just like I said, as a little gag on the side, the obvious real answer is when you remember the 2-cell copper cavity from before, what we do in a nutshell is we make those resonators cool. We actually make them super cool, as in superconducting. And superconducting RF, SRF, means that you have no losses. If you operate these normal conducting machines, you will generate a lot of heat on the surface of these cavities, or in the outer shell of these cavities, the copper normal conducting material, when you introduce that RF field. That RF field, like I said, an electric field, will generate currents in the outer shell and the metallic resonator. And those currents in a normal conductor will generate ohmic heat. And therefore, you have a lot of heat that you have to cool away. You have quite some losses when you want to accelerate your particles in the cavity. The big advantage of superconducting RF is you use a different material, niobium. Down here, you see this resonator. It becomes superconducting. And I think most of us then know superconductivity main advantage is you can conduct your currents in there with no losses. If you're talking about a DC current, at least, there are absolutely no losses. That's the definition of superconductivity. In our case, with the RF fields, we have still a very small, usually in the range of nano-ohm resistivity in those superconductors to an RF field. So we still generate a little bit of heat, but it's significantly less than you would generate with a normal conducting machine. So we're typically talking about a 99% power conversion efficiency from the RF power we introduce in such a resonator into beam power when we bring in the electrons and accelerate them in those structures. When you then ask, what does SRF look like on a large scale, then I just started you off with superconducting cavities made out of niobium. That's a elemental superconductor, and we like to go with high purity niobium. And then we have to get those cavities, you see over here, still superconducting, so we have to cool them down, as I said, super cool them down, and that we do with cryogens, and that means we have to introduce liquid helium, and that's what exactly this 9-cell cavity, you count here a total of 9 cell over here, looks like in operation, because it will be put into a titanium helium vessel around it. Over here is a connection that hooks it then up to the cryo plant inside our cryo module. That constantly provides liquid helium inside the structure here, cooling down the niobium resonator to remain in superconductivity and run without these low losses or almost zero low losses when we accelerate the electrons in that machine. The whole thing then is brought into something that is a little bit of a large scale, highly efficient refrigerator, because that's a cryo module over here. This is a structure where we have 8 cavities in total in that module. In our, again, you see Jefferson Lab, SRF Institute, when we lift those entire systems to get them on a truck, to get them out of the hall, actually, you have, like I said, on the outside, this cryo module is like a refrigerator at home. You can touch it. Obviously, it's at room temperature, and that's what it looks like when it lives in the tunnel. And on the very inside of that machine, you have those superconducting cavities, these structures that are living down at almost 0 Kelvin. So typically we operate them at 2 Kelvin, meaning that's actually cooler than outer space. If you go into outer space with a spaceship, it will be slightly warmer than those 2 Kelvin. So that's really, really cold. And hence, like I said, the comparison to your fridge at home, when you want to open your fridge and you sit inside your freezer, or put your hand inside your freezer, obviously that's really, really cold. At the same time, you can touch your refrigerator from the outside. So that's the magic, what we try to accomplish in the SRF Institute, build these cryo modules with super cool cavities on the inside, but still room temperature on the outside, so we can put them in a tunnel and operate a particle accelerator. Like I said, to operate those, you need these cryogens, you need your liquid helium, and that's again a picture of our, and it's actually one of the largest in the world, cryo plants inside the CBAF accelerator that operates this. And all that now makes it, as I said, also 12 GeV of energy, makes it really, really unlikely to use these science discovery machines as we operate here with the CBAF accelerator. And there are multiple accelerators around the world and a couple also around the US on that level. Makes it really, really not very handy or unusable for what I introduced you earlier, the treatment of wastewater. So if you want to go into something that actually can be brought outside the lab, can be used in a wastewater treatment plant to irradiate water to break down contaminants, you have to go compact. And now I want to go a little bit into what are the key technologies that allow us, like I said, I like to call the C-cube, so compact conduction cooled SRF. And one of those elements is niobium-3 tin. So as I told you before, superconducting cavities, those resonators, are typically made out of niobium. So it's high purity niobium, what we usually try to get. So if you look at your periodic table at home, this is element 41, niobium. So actually the element is an individual element, not as a molecule or alloy that has the highest critical temperature. So at 9.2 Kelvin, actually, this element starts turning superconducting. Like I said, in operation, we typically tend to operate it at 2 Kelvin, so much lower than that, to be on the safe side and be able to pump much more electric power into those resonators. Now, to enhance the capabilities of our niobium resonators, we can actually apply a thin coating of an alloy, niobium-3 tin, on the inner surface of these resonators. And this coating enhances the superconducting behavior. Critical temperature of niobium-3 tin is around 18 Kelvin, so pretty much double where your 9.2 Kelvin for niobium are. And hence you can also get higher fields in there and can operate the whole resonator at a higher temperature. The coatings of these cavities have to be done in special furnaces. That's the so-called vapor diffusion application that we're using right now, our deposition of niobium-free tin on that. And the research furnace that we have here at Jefferson Lab to do that looks like this. See in the background, this is a furnace here, and you see a couple of the operational interfaces, and there's here the utilities basically supplying from pumping down the furnace itself, also supplying all the electric power to heat it up and coat that. And the reason I'm emphasizing that here is I think there's perfect opportunity as an ANPA colloquium talk, because the expert running that at our facility is my highly valued colleague Uttar Pudasaini, who's also here in the audience. So he's, again, a very Nepali contribution to the overall very diverse spectrum of scientists we have here at the lab. So he's, like I said, the expert at our site running these niobium-free tin coating and providing the technology. And as a little Saturday morning joke, if you allow me, I took a fun picture. So this is here a picture of Uttar applying these highly sophisticated coatings. You might all know this is actually not niobium-free tin. He's applying some tika to my forehead as our recent celebration of the Dashain Festival last weekend. But to go away from, like I said, our free time activities to what it actually looks like. So we can take pictures inside the furnace. Obviously, this is a vacuum system running there at high heat, 1200 C. He has to bring these cavities up to. But this is what it looks like at the inner surface of such a cavity once he applied a niobium-free tin coating. So it's a slightly grayish coating you can see on the inside. Usually these are mirror finish, really shiny. There are different versions of the niobium-free tin coating that can be somewhat more shiny, but you can always tell just by your naked eye that you've successfully coated a cavity by looking at its inner surface. So niobium-free tin being one of the key technologies because it helps us increase the operating temperature of our superconducting resonators that we need to accelerate particles. Now going into the other side of that are CCRs, which are so-called cryocoolers. That's what such a device looks like. And what they can do is that, or the big advantage for industrial applications, let's start that way, of cryocoolers are that you can get them right off the shelf, and all they need is a gaseous helium compressor. These two, that's the inlet and outlet connectors here, basically bring in from the compressor helium gas, and in there you have a piston constantly moving up and down, managing to cool down in a two-stage process these two copper interfaces. This upper one will typically live at something like 50 to 80 Kelvin, and the bottom one down here is able to go all the way down to 4 Kelvin. I told you before, our superconducting cavities in operation in our particle accelerator machines, we typically operate at 2 Kelvin. Now that we've introduced with Uttar's help, niobium-free tin as a coating on such a cavity, we can operate at a slightly higher temperature, double more or less, at 4 to 5 Kelvin. And that's exactly where these cryocoolers come in, because they completely cut out the liquid helium supply that makes these machines very complicated when we're looking at the large-scale research and discovery machines, because you can use such a cryocooler, as I said, with a big advantage. You can buy them off the shelf from a couple of companies out there and directly connect them via conduction cooling. That's the element up here of this compact conduction cooling to your cavities. And as a consequence, no more helium and complex cryoplant is required, because that is often one of the biggest hurdles when you look at if you want to bring our particle accelerator technology out to whatever industrial application you want to use them for. And then you always need to operate your dedicated cryoplant. You need to have highly skilled and trained operators. You have a lot of maintenance that these cryoplants require. But if you build compact machines that only require these cryocoolers, they are pretty much plug and play. And that's really, again, like I said, the second biggest pillar that our idea and invention kind of is based on. That using these cryocoolers, you have an easy system to generate your cryogenic temperatures and to provide superconductivity on a small scale, at least. They obviously don't have the cooling capacity of a large-scale cryoplant, but they have a small localized option to provide cryogenic temperatures for utilizing superconducting technology for particle acceleration. And this brings us to the final section of this. Like I said, compact conduction cooled SF accelerator. I like to say the idea is born, and one of the main innovators at our lab is my supervisor, Gigi Giovati, who back in 2018 started investigating this topic, like I said, combining the niobium-free tin coating from our expert Uttar to the cryocoolers on the other side. And there's a first concept that he developed back then in a publication in 2018. So he actually started even before 2018 of what such a compact machine could look like. And you start again kind of, if you go back to my simple example where I tried to explain RF particle acceleration with your light bulb system over here, so the thermionic gun generating free electrons, you have a little bit of a DC voltage to give them the first kick, and then you enter up in the heart of the whole system, which is your cryo module with a superconducting cavity, boosting that electron out to higher energies. And over on the other side, here in the end, you have a so-called beam exit window. So that's very similar to what you've seen on those South Korean or Chinese installations to treat the industrial wastewater in the textile industry. So that's really the same kind of interface in the end that you can now pass by water and irradiate with that technology. The heart of that, like I said, is the cryo module, and here's a little cross-section image of what the cryo module looks like. In this particular design, Gigi was trying to develop a machine that was targeting a 1 MeV, 1 mega electron volt output of the machine. So very similar to the machines that I showed you earlier, like I said, based on the 70s Russian design technology. Hence, you only need a single cell cavity here in the center. And then different from the cavity I've shown you earlier, which has the helium vessel around it, this cavity has actually copper plating on its outside and on like these physical, very thick connections or conduction cooling connections to the cryo head or the cold head here of the cryocoolers. There's a cross section, as I said, you have a total of 4 cryocoolers. There's one full you see in the center, there's one cut in half, and then obviously here in the outside the picture plane you will have yet another one, and there's a 4th one on the bottom. And these 4 with their cold heads, or the second station here down at 4 Kelvin, combined cool down this cryocooler. Also one actually in the center, it cools down the beam pipe behind it because we'll bring in the RF power there. So it'll also generate a little bit of losses that we have to cool away using copper plating on the outside to conduct the heat away from the cavity, keep it superconducting, and then you can go through in this compact machine. The big difference and benefit SRF is giving you, because you might ask me now, well, John, you showed me earlier the existing machines based on the 70s technology from Russia, they can deliver already 1 MeV of electron energy, but as I also told you, they're limited to something like some tenths of kilowatt. This design that Gigi and his team developed in 2018 was already targeting an output energy of 1 megawatt. So you really have a significantly higher energy, and that makes this technology much more feasible to be used in large-scale facilities with much more throughput, because you can basically irradiate and deliver the same dose, give that to your water and your contaminants in there in a much shorter amount of time. I mean, there's a factor of 100 between your 10 kilowatt of the currently existing or in-use technology and this technology going up to 1 megawatt. So that's the key application, which is pretty much following the innovation on the science side. Like I said, these Budka Institute of Nuclear Physics developing their particle accelerator in the 70s, they also used that for nuclear physics experiments. We now, in the meantime, in the science field, have advanced to superconducting technology to have higher beam power, to have also higher energy. And now we're trying to bring that back to the industrial applications using superconducting technology to go for higher powers for these wastewater treatment plants. Now, to show a little bit what we're doing on the actual development of technology, so the ongoing R&D efforts, and we do have a strong collaboration with a collaboration partner over on the West Coast, General Atomics. They work on a lot of government-funded projects for different technologies, and one of that is actually also our technology. And over here is a cryostat actual hardware. This is, again, the CAD model. What you see next here is a picture of the inside that Gigi developed with them. And in here, you see it was just a proof of principle demonstration of, again, exactly a single cell cavity, copper plate on the outside. So under this copper coating, you have actually a niobium cavity. And on the very inside, you have your niobium-free tin layer. And you see here, this is also the second stage. You see another one of a cryocooler. And you see in this technology has these thermal straps made out of pure copper. It's a multi-layer flexible unit, actually. And you have the bulk solid copper around the cavity itself that connect this cavity to this cryocooler. And with that, Gigi was able, there's another picture of the facility over at GA, to operate this cryo module and demonstrate as a first proof of principle demonstration that we can have SRF technology delivering the same accelerating gradients for the electrons without any helium. So that was also a first of its kind demonstration of the single cell cavity with a highly usable gradient for the actual industrial application. Now, moving forward, we also tried to pick up again the investigation of what e-beam can do with water. And our big collaboration partner here locally in Virginia is the Hampton Roads Sanitation District. So they run for the area here is called the Hampton Roads. combining multiple cities, among those also Newport News. They are basically in charge of cleaning our wastewater, so the everyday household as well as the industrial wastewater. And in a collaboration with them and a PhD project on their side and PhD project on our side, we utilized one of our small accelerators we had in-house and set up a beamline you see over here. And what I'm trying to emphasize in this is actually this target rail on the end. We had these aluminum blocks, and in those aluminum blocks, you see maybe in the picture here, there's basically a hollow cylinder. We would close them up, and that's a close-up of what the experimental setting would look like. We close them, you see this little cork plug on the top, and then provided by HRSD would fill wastewater samples in there with certain contaminants, expose that to the beam. So this target rail here is movable. So we had 4 targets on that rail. There's a calibration target in the center, which we basically use to see that our beam really covers the area it's supposed to cover. And we would move one of these targets in front of it. And with that, we could demonstrate how we can break down chemicals. And that was even beyond the contaminants that Bill Cooper looked at back in the 80s at the Virginia Key Wastewater Treatment Plant in Florida. So that's also, just as a little bit of background information, you might understand or have heard that there's also new contaminants. There's obviously a technology development on the one side, but also a exploration development on the site when it comes to treating wastewater and the new threats, so to say, to wastewater. Chemicals is a buzzword there. In this particular case, 1,4-dioxane is a chemical that has become more and more popular in a lot of products and significantly increased its concentration in our wastewater from the 80s, where it wasn't so much of a problem, to nowadays in the 2020s, where we have an issue with that contaminant in wastewater. And it's basically why HRSD also jumped into this collaboration to say we have a challenge, we try to figure out how to break that down. And we could demonstrate with this experiment that we can utilize electron beam to break down these contaminants in the wastewater. Also on the other side, what I like to say, because we got a couple of grants, is the PR work on that end. Besides me giving a talk here, for example, in your colloquium, we also recently received a larger grant that has then, as a consequence, received quite some attention in media, mostly also in the local media on the Virginia pilot. We had a project collaboration. Again, you see here Uttar's furnace in the background, where we got a $7.5 million grant to develop or advance this technology towards actual application. That's news coverage here in the local Virginia pilot. Then we had yet another coverage by, I think that was in the end, the Virginia Business Magazine, where they again took a nice picture of me in the foreground here of our SRF Institute. We're trying to, like I said, as you see in the background, we built a lot of big accelerator modules for different projects around the nation, but we're trying to introduce this compact accelerator technology. Local news media was also National Public Radio, the National Public Radio that gave a coverage on that. So that's, so to say, kind of what I've been quite busy with over the last couple of months to cover these different media aspects and try to get the technology out, because we really understand what we want to build something in a research lab and bring it out to public application. We also have to do the groundwork of getting people interested in that and sort of educating people about what this technology actually does and why they don't have to be afraid of it. But exactly this very grant that we got there is also funding advances in the actual progress of that. And that's sort of what I like to call the future of compact conduction-cooled SRF. And in that one, we've actually partnered up with a couple other national, or one more national lab and a couple other national institutions. So Jefferson Lab, us, is the leading institute in that part. Fermilab outside Chicago also has a lot of SRF expertise and also expertise in an albumin-free tin coating, are joining us as a collaboration partner. And then the Florida International University is bringing in a lot of expertise when it comes to the chemical analysis of the water before and after radiation. We're trying to explore how these contaminants are being broken down to understand the full picture of our technology and obviously document that towards our funding agencies to motivate them to develop that technology. And just as a little peek behind the curtain, that's one of the latest 3D cut models of the design of what such a machine now targeting exactly the earlier mentioned threshold of 10 MeV. You might recall the machine design I showed you earlier that Gigi developed in 2018 was targeted at 1 MeV, and now we're trying to go up to the threshold, not crossing it, staying on the safe side, but just about 10 MeV of electron beam energy, so you can penetrate the water actually somewhat deeper. This is the first conceptual design of what such a machine can look like, where you have now a 5-cell cryostat at its center. And again, this is sort of the core of the whole design, a 5-cell cavity with multiple cryocoolers via conduction cooling. You again kind of recognize these thermal straps over here to the second stage of those cryocoolers that are cooling this cavity down. We have the introduction of RF power here on the one end, and the electrons will come out the other end. We've seen the picture before, then this big beam delivery horn. So it also becomes a challenge if you target these high powers, obviously to distribute that. But it also opens up, you can go to much bigger beam delivery systems and deliver much more dose to more water. So again, you really tackle the problem of increasing the throughput of such kind of a treatment facility. And that's pretty much where we are right now. We are on the conceptual side, but we're also developing more prototypes and trying to bring in this technology. So that brings me to my conclusion at the very end to wrap this whole thing up. I hope I convinced you of also a little bit, besides the history, the very current application of cleaning wastewater with electrons. Like I said, some buzzwords that come up in that field, also a shift from the 80s to what we have to tackle in our days now are PFAS, or in general, these forever chemicals, and lots of pharmaceuticals that have really gone up in the concentration in our wastewater stream. And on the technology side, like I said, we want to combine our Win15 on the alloy coating side with the cryo coolers to generate this compact conduction cooled SRF set. Just emphasizing that here for this ANPA Colloquium with a significant Nepali contribution on our end here at Jefferson Lab towards the now Win15 technology. And that's kind of my sales pitch at the end. That I say, obviously, we here at Jefferson Lab for our science mission historically are experts in building particle accelerators. So we're now looking at our lab mission. So I quoted that somewhat earlier, trying to address those societal issues, treatment of wastewater, using the know-how, the knowledge that we've developed on the science side of building accelerators. And therefore, we want to bring the state-of-the-art accelerator technology to these environmental applications in small, compact conduction-cooled machines. And that concludes my overall talk. And with that, I can give it back to Pashpati. Just got one more last on meme at the very end. That's one of our treatment facilities inside where we actually heat treat cavities. So this is not where we do the coating, but heat treatment of cavities on that end. So many thanks for your attention. And I also want to acknowledge with quick contribution of all of our collaboration partners, Bill Cooper himself, Bill as a senior consultant being involved. I mentioned him early in the talk. With that, I give it back to you, Pashpati.
Yeah, thank you, John. It was a very nice, interesting talk. That's me on the last slide. I don't know. Anyway, if anyone has a questions, audience, you can unmute yourself and ask the questions.
Hi, very nice talk. I missed some of it, but yeah, I have a very short question just for my curiosity. Nothing to do with this superconducting and all those things, but this is Jagan from Pittsburgh, and I have my question. I've been doing a little bit of work in radio frequency, microwave, but all those at ambient conditions. My curiosity is, how does the property of this electromagnetic wave or microwave radio frequency range changes as we go to low temperature for your application from those at ambient condition, or nothing at all?
So the pure radio frequent wave that you inject into your resonator doesn't change at all. As long, I mean, you keep it in vacuum. Of course, you always have frequency shifts when you pump down your cavity. We have to, and this is true for both normal conducting RF technology as well as superconducting RF technology. We have to maintain a very good vacuum inside those resonators. Otherwise, your electron or proton bunches, for that matter, would collide with RAS gas in there. So you always have to pump it down. Actually, SRF tends to make that a little easier because once you kind of cool down the cavity itself, it acts as a cryopump, as it just freezes out any remaining gas on its inner surface. But independent of that, you have vacuum in there. You put in your RF wave. The radio frequency field does not care what temperature you're at. If it is in vacuum anyhow, there's no impact of temperature.
Okay, so the medium you are doing, say vacuum, if you're doing all vacuum, that is fine. But I was thinking more like if you have some gas field in there, then the density of the gases with temperature can make the medium different. So that could have some impact on the propagation itself. But yeah, if you're doing in vacuum, then that's a different story, I guess. Yeah. Thank you so much. Yeah.
No problem.
Yeah, you can create in plasma. Yeah, so if you have if you're not in vacuum, so
okay. Yeah, all right.
That's the another thing is going on around here. So basically, we use the plasma to clean basically the cavity inside.
Oh,
We can, so that
I see.
we have to, so that's, it's very important actually that those inner surfaces of our resonators are as clean as possible. And sometimes when over time we generate contaminants inside the cavities, now we're not talking about contaminants in water, but inside the cavities because of other elements along the beam line, we sometimes have still valves somewhere that have sort of rubber gaskets in it that disintegrate due to the radiation over time. And in CBAF, there's a big issue, and we have contaminants inside those cavities that basically impede their the fields that they can reach, and then we intentionally inject gas, clean gas, dry gas into the cavities, put in the RF power again without any particle beam, but then ignite a local plasma that helps us to clean up those contaminants. But yeah, I mean, that's for example, where you have a very different impact. You have to look at where you're at with temperature. Well, how does that impact your plasma? And then we try to shift around with frequencies to target individual cells. So it's really kind of a flushing out or cleaning out those cells in situ in the machine. But that's completely separate from the operation. The actual operation, when you want to generate your particle beam, and it's also true for a compact machine, you will have to maintain best vacuum you could generate. Fun fact I mentioned before, the 2 Kelvin cooler than outer space. The vacuums, we usually operate at 10 to minus 9, 10 to minus 10 millibar in those resonators. It's actually also better than outer space. So we tend to have better vacuum in our machines than you would face if you go with a spaceship to the moon.
Okay.
Thank you. Thank you.
Thank you, Jagan. Any more question here? So okay, go ahead.
Oh, thank you, Dr. Vennekate, for an excellent presentation. I have a quick question. Like, so what is the energy of the output electron beam before you start reducing that? What is the maximum energy production?
So for our compact machines, we're looking at, like I said, 10 MeV is this threshold. We don't want to go beyond that because then we would start activating the water in terms of radioactive.
Okay, so great. So how cost effective will it be, like for, like, I mean, of course, for the large scale applications, like, of course, that will be good. But like, for example, if I'm thinking of my country, like Kathmandu Valley, let's say the river water should like, which has all kinds of contaminants, like how cost effective will it be? Just curious.
So that really varies. That's something, like I said, Bill Cooper already in the 80s tried to shine a light on. It really varies with what contaminants you're trying to break down. We are now, I mentioned the buzzword of PFAS, forever chemicals. That has gotten a increased intention of our funding agency as the Department of Energy, because they see, especially in the US, we have new regulations on that end, enforcing the cleanup of those forever chemicals in the drinking water supply. So in that case, we realized we actually need higher doses. So in that case, the chain of treatment is not you use all your water, wastewater, and expose that to electron beam, but you actually have to do a pre-concentration. There are mechanisms for that now to kind of filter out these PFAS forever chemicals and then treat them separately with the electron beam because they require a higher dose. In that phase, we are exactly, this is kind of ongoing R&D to see how competitive that is compared to other technologies to break down these PFAS, which are actually pretty limited. But there are quite some innovations popping up recently. If you look then at the non-forever chemical contaminants, using, for example, the example that I've shown you earlier of contemporary use of electron beam at South Korea and China on those industrial wastewaters where you have a lot of chemical contaminants from the textile dyeing process, you need significantly lower doses. Therefore, you can, and as they've shown, you can really envision your entire water stream passing by your accelerator and giving it a small dose. And that's, I mean, it goes down to numbers. We have some numbers, actually the 2018 publication of my colleague, and I got this here on my slide, of Gigi Giovati. He ran some numbers for his 1 megawatt, 1 MeV single cavity or single cell cavity system, where he ends up with a couple of cents of treatment cost for, I think that it was the cubic meter of water there. But these systems are competitive on that end. It always, like I said, really depends. So it's hard for me, obviously, to give you a concrete number of you're going to pay. Always depends on your local electricity and utility cost too, but how much you're going to pay for treating this much of water. But you can see already by the example, like I said, over in China and South Korea, that especially for industrial wastewater, this is already competitive and in use. Actually, in the plant, as far as what I read on the 2020 facility over in China has been installed there, what they do is they can reuse that water 7 times. So they use the water for the textile dyeing process, irradiate it, and can reuse it 7 times before they have to go to a higher or more sophisticated, longer treatment chain of cleaning up that water. So it always depends on that. But it is obviously also, and I need to emphasize that, it's not a technology where you can say just electron beam replaces everything else you need for treatment to generate drinking water. It's not the dream of let's take really dirty water, expose it to electron beam, and then you have potable water on the other outcome. It's always going to be one tool in a combination of multiple other tools to treat wastewater.
Yeah, thank you so much. And also, I would like to thank you for highlighting the contribution of Nepali scientific community at Jefferson Lab. Thanks.
All right. Any more questions? Yeah, as John already said that, like, it's not like only thing, it's one of the thing that can decompose those contaminant that cannot be decomposed other way around. So basically, I would say that way. So the last resort is electron beam, right? That's correct, John?
Well,
PFAS kind of things.
For forever chemicals, yes, it is really.
Yes.
We recently had a DOE-wide workshop on that, and there's a lot of technology development on the filtration and separation side, and it's quite limited when it comes to really a final mineralization, so breakdown of PFAS into its elements. That there are not many options out there, and this is one of them.
Okay, this is great. I don't think there is more any questions. So let's thanks the speaker. Thank you, John, giving some your early Saturday morning to Nepalese community. We highly appreciate it. And then as you can see that, and we work together. So basically, so.
Yep, and as you said, also